Hey, Dr. O here, and welcome to this mini lecture on naming acids. In this video, we're going to determine what makes a compound an acid, define the two general types of acids and learn the rules for naming each, and work through a few naming exercises to lock that information into your noggin. So, let's get started. To name acids, you're going to have to know a few rules, but the very first thing you need to be able to recognize is that the compound you're dealing with is an acid. So what is an acid? Well, in the most broad terms, an acid is a molecular compound that forms hydrogen ions in water. And if it's a molecular compound, what does that mean? Well, it means it's made of nonmetals. And if it's forming hydrogen ions, then it's a molecule that's going to be composed of hydrogen and at least one nonmetal. And usually the hydrogen is going to be written in the first position of the formula, so that's another clue that you're dealing with an acid. Now there's two general types of acids. One type is the binary acid, which is made of hydrogen and a nonmetal. And the other type is the oxyacid, which is made of hydrogen, a nonmetal, and oxygen. And there's going to be rules on how you name each one of these. So to review what we just said, the first thing you do when naming an acid is determine that it is one. Typically the formula is written with hydrogen in the first position, but this is chemistry and the rule of always doesn't apply. Usually that's true, but not always. Then you have to make a determination. If your formula is made of a hydrogen and a nonmetal, then you have a binary acid and you're going to follow the naming rules for binary acids. Or your formula is going to be made of a hydrogen, a nonmetal, and an oxygen, in which case you have an oxyacid and you're going to be following those rules for naming. So let's see what's involved with these naming rules. Naming binary acids is actually pretty simple. The name is going to take the following form. You take the base name of the nonmetal in your compound and you're going to give it that ic ending, that IC ending. And then you're going to add hydro to the beginning and then you're going to add acid at the end. So let's take a look at a few examples. Here we have HCl. Our nonmetal is chlorine. Its base name is chlor. And we're going to give that IC ending, making it chloric. And then we're going to add hydro to the front of it, and then we're going to give it that acid ending, and we name HCl hydrochloric acid. How about this fellow? Well, our nonmetal is bromine, and the base name is brome. And we're going to give that ic ending, making it bromic. We'll add the hydro to the front, give it that acid designation at the end, and we have named HBr hydrobromic acid. And there's room on the slide for one more, so let's take a look at this guy. So what do we have here? Well, our nonmetal is sulfur. And this one's just a little tiny tricky, not bad, because its base name is actually going to be sulfur, which means we're going to add that IC ending to the word sulfur, making it sulfuric. We also going to go ahead and add that hydro to the beginning and the acid to the end, and we can name this guy hydrosulfuric acid. And that, my friends, is how you name binary acids. So what about oxyacids? Well, oxyacids are made of oxyanions, which are simply polyatomic ions that contain oxygen. And you'll find these in any polyatomic ion chart. Oxyacids are made by combining hydrogen with that oxyanion. Because we're talking about anions, we have to think about balancing charges when writing the formulas for these oxyacids. So you may see compounds with more than one hydrogen in the formula. So here we have HNO3. It contains the nitrate ion, which has a -1 charge. And this is going to be offset by the positive charge of one hydrogen ion. Here we have H2SO3. The sulfate ion has a -2 charge, and this is going to be offset by the positive 2 charges from 2 hydrogen ions. H2SO4 also contains a -2 charge. This is the sulfate ion, and these are going to be offset by the positive charges of 2 hydrogen ions. Before we get too far along, I want to review some polyatomic ions, which is what we can do with this chart right here. So if we take a look at some of these, we can see that for the most part, these ions have an ite or an ate ending. So what's the difference, you might be asking yourself? Well, if you notice, you'll see that a lot of the oxyanions are in a series. That is, their formulas differ by one oxygen. That makes them different compounds, right? So we have to communicate that, and we do so by these endings of ite and ate. The ite ending is given to the ion with fewer oxygens, and the ate ending is given to the ion with more oxygens. What this doesn't tell us is the number of oxygens, unfortunately. It only tells us that we have two in a series, and one has more oxygens and the other one has less oxygens. So let's take a look at a couple of these. Let's look at these right here. Here we have chlorine and some oxygens. ClO2 is called chlorite, whereas ClO3 is called chlorate. And over here we have SO3, which is sulfite, and SO4, which is sulfate. Now this naming system, like I said, doesn't tell us how many oxygens is in the ion. It's just letting us know that there are relative amounts, that one has more and one has less. So why do I bring all of this up? Because those ite and ate endings mean something, and we're going to communicate that when naming our oxyacids. So as we just saw, you can have more than one species of oxyanions in a series, like nitrate and nitrite. Nitrite has 2 oxygens, whereas nitrate has 3 oxygens. So what are the rules for naming these oxyacids? Well, if the oxyacid is made of an ion that has an ite ending, the acid retains the base name of the anion but gets an us ending. If the acid is made from an ion with the ate ending, the acid retains the base name of the anion and gets an ic ending. So let's name our nitrate and nitrite acids. If we make an acid from nitrite, its formula will be HNO2 and its name will be nitrous acid. If we make an acid from nitrate, its formula will be HNO3 and its name will be nitric acid. And there you have it, the rules for naming oxyanions. Let's try our hand at applying these rules for naming oxyacids. So we've got a couple of oxyanions. We've already seen these before. We have chlorite and chlorate. And to name an acid made from the chlorite ion, it would be chlorous acid. And to name an acid made from the chlorate ion, it would be chloric acid. Now here we have 2 oxyanions made with sulfur. The sulfate ion would give us sulfuric acid. So a little bit different with the name. We're actually including the entire name of the element and giving it the ending. So sulfuric acid, and to name sulfite, an acid made from sulfite would be sulfurous acid. So a little bit of variation, not a big one, but you know, can make a little mistake there. What about this guy? We have just the lone phosphate ion, but we can still more or less predict its name, right? Well, you might assume that it's going to be phosphoric acid, but we're going to add a few more letters, and it's actually going to be phosphoric acid. Not a big deal. I think only a hardcore dyed-in-the-wool IUPAC acolyte would frown on that kind of mistake. What about this character? Well, he's actually going to follow the rules, and he becomes acetic acid. That's right, good old vinegar. And the last one, carbonate. If we were going to form an acid with this guy, it would be carbonic acid. Here's a question for you. What's the difference between hydrochloric acid and chloric acid? Well, think about the names. They both have chlorine, and they're both acids, so there's going to be hydrogen, right? But what does the prefix hydro tell us? Well, it tells us that hydrochloric acid is a binary acid and that it's going to be made only from hydrogen and chlorine. Now, chloric acid has that ic ending, with no hydro, and that's going to mean it's an oxyacid. The name tells us a story if we pay attention. So without that hydro prefix, not only does it contain hydrogen, but also oxygen. And that ic ending is telling us that there's more oxygen there than there would be if we'd used another oxyanion. I know, isn't this crazy? Although it doesn't tell us exactly how many oxygens there are. Nevertheless, both of these names are designed to communicate the traits of the compound to the reader. And with that, we are done. Thanks for watching.